All right, so for IQA number 8, the first question is, why is the Mach number of a converging nozzle limited to 1? And so this can essentially be derived via the mass flow rate. And so the mass flow rate is limited by the inlet pressure and temperature. And so we know there's a maximum mass flow rate. And at that maximum mass flow rate, the rate of change of the mass flow rate with the rate of change of velocity will be 0. And so if we take the derivative of this with the derivative of velocity, which in this case is the Mach number, or is represented by the Mach number, we get, and then we set that to 0, we can solve for the Mach number at the maximum mass flow rate, and we get a value of 1. And so for the maximum mass flow rate, since the Mach number is 1, and the Mach number will not increase more since the mass flow rate governs what the velocity will be for the converging nozzle area, we can say that the Mach number, or the maximum Mach number, is equal to 1 for a converging nozzle. Now for question 2, find the inlet temperature and pressure necessary to accelerate air to the speed of light in a converging nozzle that vents to the atmosphere. Assume gas constants are constant at the value for 25 degrees Celsius. And this assumption is essentially necessary because the gas constants are not actually constant with temperature. In fact, Cp, Cv, and therefore K all increase with temperature. And since the temperature for this problem will be incredibly high, it would be incredibly difficult to estimate those values. And so we essentially have to estimate it at a value. And for this problem, it's chosen to be the values for 25 degrees Celsius. And so we know that the exit velocity is the speed of light. We're told to find the inlet pressure and temperature. We can assume steady state. The Mach number at the exit is equal to 1. This is essentially to minimize the pressure and temperature differentials over the nozzle. We can say the inlet velocity is negligible because we're given no information about it, and that R, K, Cp, Cv are all constant with a change of temperature as set in the problem. We get all of our constants from the table, and the speed of light is 3 times 10 to the 8th meters per second, and atmospheric pressure is 101.325 kPa. And so we essentially start off with the Mach number of 1 equal to velocity over speed of sound. And so we find that the speed of sound equals the velocity. And so as we know what the velocity is, we can calculate the speed of sound. And then from that, we can calculate the exit temperature based on this formula here. And then from that, we can calculate the stagnation temperature based on the exit temperature and exit velocity. And since the inlet velocity is negligible or 0, the stagnation temperature equals the inlet temperature. And then from the stagnation temperature and the exit temperature, we can get the stagnation pressure. And then since the stagnation temperature and inlet temperature are equal, this value goes to 1, and the stagnation pressure equals the pressure in. And so we get both of those values right here.